Okay, today in this lesson, today we'll be working on two concepts. One is linear approximation and another is differential. So we have two concepts that we'll be talking about in today's class, okay? So um, basically what we do in this unit is we examine, another application of derivative, the ability to approximate functions locally by linear functions. So I think you know what this linear means, right? So linear functions are the easiest functions with which we can work, okay? So they provide a useful tool for approximating functional values. So basically by the end of this class, you will be able to describe the linear approximation to a function at a point, and you'll be able to write the linearization of a function, of a given function, and calculate the relative error and percentage error in using a differential approximation. So these are the three goals for today's class. And all of these goals revolve around the fact that, around the concept that I just mentioned, linear approximation and differential, okay? First, let's begin with differential. What does that mean? So for a function, y equals f of x, whose derivative exists, the differential of x written as dx is an arbitrary real number, usually small compared with x. The differential of y written as dy is given by this formula. So basically what I'm saying is that if we have a function y equals f of x, okay, then can I write this dy over dx equals f prime of x? Can I write that? So everybody know that I can write this, right? So with little algebra, I can write dy equals, multiply both side by um, dx, so that you will get f prime of x dx. So this is called differential. Okay, so the dy is called differential. Now there are um, and then the application of differential is that what it means is when there is a change in x by dx, so dx means it's a small change in x, and what will be the corresponding change in y? So the corresponding change in y will be dy. So that's what it means, okay? So when we are given a function, let's say, let's go all the way to the example one. Given the differential dy, sorry, find the differential dy for the given values of x and delta x. So we are given a function y equals 2x cubed plus x squared minus 4x, and then x equals 2 and delta x equals negative 0.2. Now remember, dx and delta x are equal. Okay, why they are equal, we'll talk about that later. So at the moment, just remember that delta x and dx are equal or approximately equal, if you want to say that way, but they are basically equal. Now find the differential dy for the given function. So what is given here is y, let me just copy that, 2x cubed plus x squared minus 4x. Now I want you to find the derivative dy over dx, which is 6x squared plus 2x minus 4. And because we want to find the dy, so you can write this as dy equals 6x squared plus 2x minus 4 times dx. Okay, with little algebra, we can write this down. Now substitute the values of x and dx, or you can say delta x. Okay, they are equal. Let us substitute the value, and what do we get? Okay, Kuldeep, thank you. And if I substitute the value, so dy equals 6x is given 2, x is given 2, and delta x is given delta x is given to be negative 0.2. So if you
2 square, please. 6 multiple
sorry,
2 square.
thank you. I was checking how many of you are paying attention. Thank you so much. Yeah. So altogether, you will get negative 4.8. Is that correct? Everybody got that?
Yeah, got the same.
Okay, so it must be correct, right? Because we already said that if we get the same answer, probably the answer is correct, because it is very difficult to get the same wrong answer, by the way. Anyway, now we got this dy is approximately, or it's actually, you can write equal negative 4.8. What does that mean? What is the meaning of this? What it means is when x is 2 and then the new x is, let's say, x1, the new x is, there is a change in x by negative 0.2. So you can write the change in x, which is dx, is negative 0.2. Then what will be the change in y because of that? So the change in y will be negative 4.8. If there is a change in x by negative 0.2, then the corresponding change in y will be negative 4.8. That's what it means. Okay. All right. Now let's try a few more questions. But before we move forward, let's go back to the concept of linear approximation, and we'll see how these differential and linear approximation are connected, and then we solve the remaining problem. Okay, guys? What is linear approximation? Well, you can see two figures here, right? Let me just work with this second figure now. In this figure, you see that the blue line is a function. This is the curve represented by f of x, or y equals f of x. And at the point A, x is a and y is f of a, I draw a tangent line. And I represent that tangent line by L of x. Now, I want you to find the equation of that line L of x. So equation of tangent line. So equation of line, you already know the formula y minus y1 equals m times x minus x1. So remember our x1 and y1, the point, one point is given this. And what is the slope? Slope of a tangent line at this, slope of tangent line, which is m, slope of tangent line is given by the derivative at the point A is f prime of a. So now if I substitute the value, y minus y1 is f of a equals m is f prime of a, x minus x1 is a. Okay, x1 is a. So basically the equation of a tangent line equals y equals f of a. I bring this, f of a to the other side, it will be positive, plus f prime of a and x minus a. So this is the equation of a tangent line. And generally we represent that by L of x. Okay, so this y, you can write y equals this, but generally we represent this tangent line by the symbol L of x equals f of a plus f prime of a x minus a. Okay, generally this equation is represented by L of x, which means this. So what we are trying to do in this section is that, first of all, dealing with the curve and dealing with a straight line, always dealing with a straight line is easy, right? Even to find the equation of a straight line is pretty easy. We just use the formula y minus y1 equals m times x minus x1. But if I ask you, find the equation of this curve, it's not easy, it's not fun, right? It's complicated. So the straight line is the easiest curve, easiest, you know, curve that can be dealt with. I mean, in a very easy, in a convenient manner. So, um, and then the idea here is that the value of the curve and the value of the tangent line around this neighborhood, if our neighborhood is very small, okay, delta x, for example, a to delta x is, let's say, this much, very small, then in that neighborhood, the value of the tangent line and the value of the function are approximately the same. So what we want to do is, instead of dealing with the curve, which is a little bit difficult, we will deal with the straight line, and we find the value on the straight line, and then we say that this is approximately equal to the value of that given function. So that's the whole idea in this case. Now let me go back to this figure. So what is the difference between delta y and dy? And what is the difference between delta x and dx? So let's see the difference between these two things, okay? Is there any difference between delta y and dy? Remember, when we say dy, it means always this, we're talking about the tangent line, because dy over dx is slope of the tangent line, okay? So dy means we are talking about tangent line, and dx also means we are talking about tangent line. And delta y means actually the change in y, the real change in y. So look at this figure. The function is represented by blue line and the tangent is represented by red line. And we consider a point x equals a here, which means this is a and f of a. And now let me go delta x further on that. So this point is a plus delta x. Now this value will be a plus delta x and f of a plus delta x. So that is the point. Okay. Now, notice that the exact difference between y is, earlier this is your y. And now the new y is this. So the change, actual change is this one. That is the actual change in y. Okay, makes sense? So looking at this figure, the actual change is this. This is delta y. And if I draw a tangent line, as you can see, then from here to here, this is your dy, this part. From here up to the tangent line is dy, up to the function is delta y. From this point up to the tangent line is dy, this is dy, and up to the function is delta y. So that's the difference between delta y and dy. Now, what is the difference between delta x and dx? So this is delta x as well as dx. So dx and delta x are always equal, whereas dy and delta y are approximately equal, depending on how big of a value that you consider. If a is here and you consider delta x of this length, then you can see, even though dy and delta y are approximately the same, but there is a difference. But suppose your delta x is extremely small. Let's say your delta x is just this much. Then your dy and delta y will be pretty much the same. That's the idea. Okay, now too much talking. Now let's go back to the lesson, the example 2. Is it clear, guys, before we move forward? So you see the idea why I want to use the linear approximation. The reason is simple, because dealing with the curve, dealing with a different kind of function is not easy, but dealing with a straight line is easy. So what we do is we want to find the value of the straight line at some point, and then we say that that value is approximately the same in that small neighborhood. so we can find the value of the function as well. So that's the idea. Now let's look at example 2. Suppose that f of x is x cubed and that x changes from 2 to 2.1. What is the approximate change in y? Okay, it's a good question. Also find the relative error in approximation. And here is the formula for, we'll talk about the relative error in a minute. So first of all, let us find change in y. So what is given here is the function, given the function f of x is x cubed, and you can find out the derivative, which is 3x squared. And what is also given is x is given 2. And what is the delta x, by the way? 2.1 minus 2, right? So that is 0.1 is delta x. Or you can say dx as well. Dx and delta x are equal. Okay. And now let us find dy. So here y equals x cubed, that means dy over dx equals 3x squared. And so dy equals 3x squared dx, right? So we got the dy. So that means now substituting the value, substituting values of x and dx, what we get here is dy equals 3x means 2 square and dx is 0.1. So that's going to give me, somebody help me. It is 12 times 0.1 is, I believe, 1.2. I mean, sorry, it is, yeah, 1.2. Is that right? This is your dy. Now, what is delta y? Delta y is actually the change, actual change in y. So that means delta y means 2.1 minus f of 2. So that is your delta y. Okay, this is your delta y. So f of 2.1 means 2.1 cube minus f of 2 means 2 cube. And help me, what is the value? I believe it is 1.261. Notice that dy and delta y are approximately the same, right? Now let us find relative error. Actual change in y is 1.261, but the approximate change in y is 1.2. So if we use this linearization technique, the tangent line method, then your approximate change, you got 1.2, but actual change is 1.261. So what is the error there? So there is some error, right? So we want to find the error. And generally error is represented in percentage. So relative error is dy over y percentage. So relative error percentage is this. Okay, or you can write this way too, or you can write delta y over y, or you can write dy over y if you like, percentage. Let me first write relative error and we change it into percentage later. Okay, so relative error is now dy is 1.2 over y is, oh, y is not given, so you can find y here because y is x cubed, and when x is 2, it's given there, your y equals 2 cubed, so that means 8. So you can write y is 8. Okay, even though the value of y is not given, but because y means the function, and you can actually find the y value easily. So if you divide 1.2 by 8, somebody tell me what is it? I believe 0.15. And so let us write that in percentage. So relative error in percentage. In percentage will be 0.15 times 100%. So that's going to give me 15%. That is the relative error. Okay. Now let's look at some application. What is the application of this differential? Is there any application in the real world? Because we are interested to use mathematical concept to solve problems in the real world, particularly from business, economics, and social science. That's our goal. Okay. If the math doesn't have any application in the real world, then we don't want to study that, right? So basically, every mathematics, no matter how abstract they look like, they have some application in the real world. That's why the math field is growing day by day. The radius, okay, let's look at this example 3. The radius of a sphere was measured and found to be 21 centimeter with a possible error in measurement of at most 0.05, positive, negative, plus, minus. Radius of a sphere was measured and found to be 21 centimeter with a possible error in the measurement of at most 0.5 centimeter. 0.05 centimeter. What is the maximum error in using this value of the radius to compute the volume of the sphere? Okay, you know what is a sphere is, right? It's just like a ball. Okay, so like a ball. So this is our radius r. It is given 21. So what is given is r is 21 centimeter and the dr is given 0.05. That is your change in r. Now we want to find the maximum error in using this value to compute the volume. Okay, what will be the change in volume? When there is a change in radius by 0.05, what will be the change in the volume? That's what we want to find. So we want to find dV. Now in the previous example we were given the function, we were given the equation, we were given the formula, but here it's not given, but you can write down the equation by yourself, or you can write the formula or function by yourself. So the formula is volume of sphere. Can you tell me what is that?
4/3
pi r cube.
Excellent. Yep. Okay. Now, guys, you can do it easily. I think I just leave it to you. Find the derivative dv over dr, which is 4/3 pi. R cube means 3r square. So you'll get dv equals 4 over, this 3 cancel out. So you'll get 4 pi r square. And now substitute the value. So to find the relative error, we know the formula. The formula is relative error equals delta V over V, which is approximately dV over V dV over V, which is given by dV. We already know dV, which is 2 dV is 277 over what is V? Okay, let us calculate V. So because V is 4 over 3 pi r cube, which means 4 over 3 pi r cube. R is 21 cube, which will give me, I don't know, is it approximately 38772 point? Okay, thank you. 387. Okay, so if I divide that, then how much do you get? Is it 0.00714? Am I right? Or if you change it into percentage, you're gonna get 0.00714 times 100 percentage. So that's gonna give me 0.07 percentage.
I think so.
Yes, I was checking how many of you are paying attention. Of course, this will be, if you multiply by 2 zeros, then this point decimal will go there. So that means it will be 0.7 percentage. Thank you, Q. Thank you. Okay, that's it. So the differential is done actually. So I think you'll be able to handle all of these questions. Now, example 4, I leave it to you and try this yourself at home, or if we have time today later, but I just leave it to you. And if there is any question, then maybe we'll discuss in our next class. Now, concept number 1, differential, is done. Now let's work on another concept, linear approximation. So which is example 5 and example 6 are very similar, and I'll do one of these two. Tell me which one you want me to do. And if you know how to do one, you can do another easily. So tell me which one you want me to do. No preference?
Yeah, the second one.
Okay, so let's, second one. Okay, all right. So example 6, let's work on that. So remember the formula that we have just written for linear approximation, the equation of a tangent line is this. L of x equals, do you remember that formula? F of a plus f prime of a x minus a. So what we need to know is the, is the derivative first. So let us find the derivative of this guy. Given f of x equals x plus 3 square root, which means x plus 3 power half. So your derivative is going to be 1 over 2 square root x plus 3. So that will be the derivative. I trust that everybody know how to get this. And what is a? So a equals 1 given. So your f of a will be, just substitute the value, f of a will be 1 plus 3 square root, which is 2. And what is your f prime of a means? Let me write this way. F of a equals f of 1 equals this. So f prime of a means f prime of 1, because a is 1, is going to be 1 over 2 times 1 plus 3. So that's going to give me 1 over 4. Is there any question so far?
No.
Okay, then let us write the formula. I just want to copy the formula that I just wrote there. So the formula is linear approximation is given by L of x equals f of a plus f prime of a x minus a. So that is the formula. Now let us substitute the value. So what it means is f of a means f of 1. I think we can write the value directly. So when a is, we already have f of a, which is 2, plus f prime of a, which is 1 over 4, x minus a is 1. And we got the form, we got the equation here. That is our linear approximation. Okay, or if you want to write this nicely, you can write this as 2 plus 1 over 4x minus 1 over 4, and if you simplify it, you will get x over 4 minus, not minus, plus 7 over 4. Is that right? 2 minus 1 over 4 is 7 over 4. Okay, let me write this as equation 1. This is equation 1. That is our linear approximation. So find the linearization of the function. Yes, we found it, L of x. Now the question further tells us that use this result, use this line, linear approximation, the equation of a tangent line, to approximate the number 3.98. Okay, let us approximate that value without using calculator. Okay, so to approximate square root 3.98. So first of all, our function is x plus 3 square root equals 3.98. Okay, that is the given function. And now we want to compare that function with this, whatever that we want to approximate, so that we'll be able to find the value of x. Remember, if you want to find the approximate value, you need to know what is the value of x here, right? If you substitute that value, then you will be able to find the required answer. So we need to find value of x. How to do that? Always, always consider the given function and whatever value that you want to approximate, and they are equal. Now this should give you x plus 3 equals 3.98, and somebody tell me what is the value of x. 0.98.
98.
Right, it's not difficult. Okay, x is 0.98. Therefore, now substitute the value in equation 1. So substituting value of x equals 0.98 in equation 1, we get L of 0.98 equals 0.98 over 4 plus 7 over 4. Now, tell me what is this value approximately. That's what I got. I want to check your answers with you guys. Did you get the same thing?
It's 1.995.
So 1 point what?
995.
Yeah, there is a. Can you, okay, 1995. Okay, all right. All right, so 995. I trust you guys, okay? Make sure this is the, correct.
Yeah.
All right, okay. Now, second thing, now we want to approximate. There is two questions actually. So to approximate, what is the other one that we want to approximate? Can you tell me? It is square root 4.05. Is that right? Okay. So then we will figure out what is the value of x. So that means square root 4.05. So that gives me x plus 3 equals 4.05. So this gives me the value of x equals 1.05. Okay. So substituting this value of x equals 1.05 in equation 1, we get L of x means 1.05 equals, substitute the value, so 1 x over 4 means 1.05 over 4 plus 7 over 4, and tell me what is the approximate value there. I think somebody already answered that. 2.0125. Okay, 2.0125. All right. Yeah, that's it. So that's the approximate value. Now, I would like you to check this answer using your calculator directly. So using calculator directly, just for fun, okay? It's not required. And let's see whether our answer is approximately correct or not. So by using calculator directly, square root of 3.98, how much do you get? And square root of 4.05, how much do you get? So can somebody tell me what do you get?
The same values.
Approximately the same, right?
Yeah.
Okay. So we notice that using the linear approximation, and we will be able to find out the value of the function using the tangent line, using the straight line, which is really easy to deal with. So this is all about this section, and maybe in our next class we'll try one questions, just for fun, but this much for today.